Deep in the cosmos, far beyond our solar system, a catastrophe is unfolding. A massive star, once stable and burning steadily for billions of years, has entered the final chapter of its existence. This is not a slow, gradual decline. Instead, it's a violent and dramatic transformation that will result in one of the most powerful explosions in the universe. We're talking about a stellar explosion so intense that it will obliterate everything in its immediate vicinity. In the coming minutes, we're going to explore what happens when a star reaches the end of its life, and why the nearby planets and space installations should be terrified. Let's start by understanding what we're witnessing. The star in question has swollen to enormous proportions, its outer layers expanding outward like a massive balloon being inflated to the breaking point. The surface of this doomed star is no longer the calm, steady photosphere we might expect. Instead, it's a chaotic landscape of violent plasma waves and intense solar flares. These flares shoot outward from the surface at tremendous speeds, releasing unimaginable amounts of energy with each eruption. The star's core is burning hotter than ever before, fusing elements at a rate that cannot be sustained. Pressure is building, and the star knows only one way to release that pressure: through a catastrophic explosion. Scientists monitoring this event from orbital observatories are watching with a mixture of fascination and dread. Their telescopes are capturing every detail of this stellar death throes. The equipment in their research facilities is working overtime, analyzing streams of data pouring in from satellites positioned around the doomed star. On their holographic displays and computer screens, they're tracking the rising temperatures, the increasing radiation levels, and the destabilizing magnetic fields. The warnings on their control panels are flashing red, alert after alert, signaling that something catastrophic is about to occur. These scientists know exactly what's coming, and they're documenting every second of it. The nearby planets don't have the luxury of knowing what's about to happen in scientific terms. They simply exist in their orbits, completely unaware that their world is about to change forever. Some of these planets are close enough to the star that they've already begun experiencing the effects. The radiation levels are spiking. The heat is intensifying. Planetary atmospheres are beginning to strip away as the intense energy from the star's surface bombards the upper layers. If these planets had inhabitants, they would be experiencing the most terrifying moments of their existence. Now, let's talk about the explosion itself. When this star finally reaches the breaking point, the resulting detonation will be absolutely staggering in scale. The explosion will send a shockwave racing outward through space at speeds that approach the speed of light itself. This shockwave will expand in concentric rings and waves of pure energy, washing over everything in its path. Any planet caught in the direct path of this blast will face total destruction. The intense heat will vaporize surface materials. Landscapes will crack and crumble. Entire planetary crusts will be torn apart by the sheer force of the energy release. But the destruction doesn't stop at just the immediate vicinity. The explosion will also release massive amounts of radiation across the entire electromagnetic spectrum. X-rays, gamma rays, ultraviolet radiation, and high-energy particles will flood outward from the explosion site. This radiation will strip away the protective magnetic fields that normally shield planets from cosmic hazards. Unshielded planets will face sterilization of their surfaces. Any organic life that might exist on these worlds will be annihilated instantly. The radiation will penetrate deep into planetary atmospheres and even into subsurface regions. The space stations and satellites orbiting in this region are perhaps the most vulnerable of all. These installations are filled with sensitive electronics and human crews who depend on those systems to survive. The intense radiation pulse from the explosion will fry their electrical systems. Solar panels will be overloaded and destroyed. Communication systems will be knocked offline. Life support systems will fail. Any crew members aboard these stations will face almost certain death unless they can evacuate to shielded areas, which is unlikely given the speed at which the destruction arrives. The explosion will reach these installations in minutes, leaving almost no time for meaningful escape. Gravitational waves will also be generated by this stellar explosion, rippling outward through the fabric of space-time itself. These invisible waves will compress and stretch the very structure of space around nearby objects. While gravitational waves won't directly destroy planets or stations in the way that radiation or kinetic energy might, they represent another invisible danger that adds to the overall catastrophe. Modern observatories equipped with gravitational wave detectors We'll be able to measure these ripples, but there's nothing anyone can do to shield themselves from them. The debris field left behind by this explosion will be absolutely chaotic. Fragments of the star's outer layers will be ejected into space at velocities exceeding hundreds of kilometers per second. Any solid object in the path of this stellar debris will be struck with impacts equivalent to thermonuclear weapons. Planets will be bombarded with this material. Space stations will be torn to pieces by hypervelocity impacts. Orbital debris from destroyed installations will collide with other structures, creating secondary explosions and more debris. The region around the explosion will become an expanding cloud of destruction and chaos. What makes this situation even more dire is that there's no way to predict the exact moment of explosion. The star could detonate in hours, or it could hold together for days. Scientists are watching the data streams, trying to determine when the critical moment will arrive, but stellar physics doesn't always follow predictable patterns. The explosion could be delayed, catching inhabitants off guard if they've relaxed their vigilance. Or it could happen sooner than expected, before anyone has time to react. This uncertainty is part of what makes stellar explosions so terrifying from a survival perspective. The intense heat from the explosion will also trigger secondary effects. Radiation will superheat any remaining atmosphere around the doomed star, creating violent thermal currents and storms. Pressure waves will compress any nearby gas clouds, potentially triggering the formation of new stars in the surrounding region. The cosmic environment will be completely transformed by this event. The region that was once relatively stable, where planets orbited peacefully around their parent star, will become a hellscape of radiation, debris, and violent energy. If you were somehow able to observe this event from a safe distance, the visual spectacle would be absolutely incredible. The star would brighten dramatically, reaching a peak luminosity that might outshine its entire galaxy of billions of stars. The light from this explosion would race outward at the speed of light, illuminating the cosmic darkness. The expanding shockwave would create visible rings and shells of energy, spreading through space. The debris field would catch the radiation from the explosion, creating a brilliant light show of reds, oranges, yellows, and whites, as material was heated to extreme temperatures. From a scientific perspective, this would be one of the most valuable observations a researcher could ever witness. But from the perspective of anything actually located in the impact zone, there is nothing valuable about this event. There is only destruction. The explosion will leave behind a region of space that is completely sterilized and empty. Any worlds that once orbited this star are gone. Any civilizations that might have existed are erased from existence. The star itself is reduced to a compact remnant, either a white dwarf if this is a less massive star, or potentially a neutron star or black hole if the original star was massive enough. The aftermath of a stellar explosion is a cosmic graveyard. This scenario plays out in the universe constantly. A star is approaching the end of its life and is about to undergo a similar catastrophic explosion. We are fortunate that our own sun is nowhere near the end of its life cycle. Our sun has already burned steadily for about 4.5 billion years and has roughly another 5.5 billion years before it begins to expand and eventually shed its outer layers. But for any civilization that might exist in the vicinity of a dying star, the situation would be absolutely dire. There would be no escape, no negotiation, no way to prevent the inevitable destruction that stellar physics demands. The study of stellar explosions and stellar death has taught us profound lessons about our place in the universe. We are all made of matter that was once forged in the cores of stars. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all of these elements were created inside stars and distributed throughout the cosmos when those stars exploded. In a very real sense, we are all made of stardust. And one day, the star that created our home will also undergo a similar transformation, though that won't happen for billions of years. Until that distant future arrives, we can observe and study stellar explosions happening elsewhere in the cosmos. We can watch as massive stars reach the end of their lives and undergo the most violent transformation that nature allows. We can measure the energy released, the radiation produced, and the debris scattered across light years of space. And we can use that knowledge to better understand the universe we live in and our place within it. The explosion of a star is one of the most powerful and destructive events that can occur in the cosmos, and it should inspire us to appreciate the stability and safety of our current cosmic neighborhood.